Physics, Chapter 3, Section 1. In this chapter, we're going to be looking at the idea of acceleration, and acceleration is essentially the change of an object's velocity. So we want to use, once again, motion diagrams to be able to show objects change over time, and we want to look at the idea of acceleration. How is it different from velocity? And this time, in particular, we're going to start looking at velocity time graphs, which are going to be very important to this chapter. Recall that a vector is something that has a magnitude and a direction. We're going to be talking about vectors again, and we're going to be talking about the concept of velocity in terms of physics. We're going to look at velocity time graphs, and we want to look at something called average acceleration as well as instantaneous acceleration and see how the two differ. Objects in uniform motion move in a straight line at a constant velocity, an unchanging velocity. Obviously, most things don't move in that type of pattern. Most things move somehow else. They're either speeding up or slowing down. They're falling. They're going in a circular pattern. They're going in some kind of arc, like a baseball or a football. Now, one of the things you can tell as far as uniform motion and non-uniform motion is if you close your eyes and you don't feel like you're being pushed or pulled, then you're probably in uniform motion. If you sit in your car, you close your eyes, you don't feel like you're being pushed back into the seat, you don't feel like you're getting thrown forward into the seat belt, you're at a constant speed. But if you feel like you're getting pushed to the side or thrown forward or back, now you're no longer in uniform motion. So here we have some different examples. Here's a person standing still. Here's a person walking at a constant speed. If they're walking in a straight line, that's uniform motion. Here we have somebody that can be walking in a straight line, but it's not uniform motion, because as you notice, for each second that the picture was taken, the person is further apart from the one before them, indicating that they're speeding up. Here the person's slowing down. Motionless, equal spaces, constant speed, speeding up, slowing down. Okay, so if we graph this out and do a particle model, we'll notice that the particles get further apart. We'll also notice that the vectors, the velocity vectors are changing. The velocity vectors are either getting longer or the velocity vectors are getting shorter. And this is just saying that it's how the vectors change. Both of them will give us an idea of how the velocity is changing. For a motion diagram, though, to give a full picture of motion, we really have to include a notation on its acceleration. The rate at which the velocity changes is called the acceleration. When the velocity of an object changes at a constant rate, it has a constant acceleration. In other words, if it's speeding up smoothly or slowing down smoothly, something that's falling, for instance, accelerating constantly, we have a constant acceleration. You can use a particle model to draw these. Again, here's your particle model. We add the velocity vectors, showing the velocity vectors are getting longer. If you take any two consecutive velocity vectors and subtract the former from the latter, we'll call this one the final and this one the initial for this particular little section of time. We just subtract the initial from the final and we get a change in velocity. Change in velocity is the same as acceleration. You can determine the length of the direction, the acceleration, by subtracting consecutive velocity vectors. If we want to put it in the form of a format, in terms of a format, again, the change in velocity is going to be former minus latter divided by the time frame that you're looking at. Or another way of looking at it is you could add a negative initial vector, put it over time. So doing the calculation, since the time interval for our graphs here was 1 second, then in 1 second we change the velocity by this quantity down here, this small quantity. That's going to become our acceleration. And here we're just saying that the velocity vi and vf refer to initial and final. You need to know the direction of both the velocity and the acceleration vectors in order to determine whether an object is speeding up or not. When the acceleration of an object is in the same direction as the velocity, the object is speeding up. When the acceleration is in the opposite direction, the object is slowing down. I'm going to show you examples of this in class. So we have kind of a complex set of diagrams here. Velocity to the right, acceleration to the right means the car is going to speed up. However, if the velocity is to the right, but the acceleration is to the left, the car is slowing down, coming to a stop. If the car turns around now and the car is going to the left and the acceleration is to the left, we say it would be speeding up going to the left or in the negative direction. If on the other hand the car is going to the left but the acceleration is to the right, it essentially means the car is going left but it's slowing down. An object has a positive acceleration when the acceleration vector points in the positive direction, however we define positive, whether that's up or to the right or whatever we decide. Negative acceleration points in the opposite direction. The sign of the acceleration alone does not indicate whether the object is speeding up or slowing down. You also have to take into account where they're going. So we could start drawing some velocity time graphs. See if this will work. Nope, I guess it's not going to work. Never mind. The average acceleration of an object then is the change in the velocity during a measured or a measurable time interval divided by that time interval. In other words, if we have the velocity vectors represent a second, then we would take two velocity vectors, consecutive velocity vectors, and divide by that second. We could have a curved velocity versus time graph. In other words, this is when we're accelerating slowly and then we're accelerating more quickly. So the velocity then would give us a curved graph. I'm going to show you some other examples where we have constant velocity and we're going to get a straight velocity graph. But we have velocity is our y-axis, and again time. Remember I told you time is always going to be the x-axis when we're drawing these kinds of graphs. The slope, which again you could figure out what the slope of this line is, or if we draw a line that's tangent to the curve, we could figure out what the slope of that tangent would be for any particular interval we're looking at. The average acceleration then is measured. If you go back again to the graph, it's time, or it's rise over run, meters per second over seconds. So we could say that's meters per second or meters per second squared. They both mean the same thing. This describes something called instantaneous acceleration. What is the acceleration at that particular time? The instantaneous acceleration of an object can be found then by drawing the tangent line to the velocity graph like this. You'll see the instantaneous acceleration is changing over time. Here we have a fairly fast acceleration. Here the acceleration is slowing down. But keep in mind this is a velocity versus time graph. So now we have a positive velocity at about, well, let's call that 10 meters per second. And so that means that it's traveling away from the origin at a constant speed of 10 meters per second. It's not accelerating, but it's not slowing down either. So how would you describe the sprinter's velocity and acceleration shown in the graph? Well, it starts out and the acceleration is pretty quick off the line. As the runner gets up to speed, the acceleration drops off and becomes negligible. However, the runner is still running at a constant rate of speed. So we get a flat line on the velocity graph. If we were to draw this on a position graph, again we would get that upward angle as they move away from the origin. So if we wanted to answer that question, we could basically sketch this out. We would look at starting with 0, rapid, increases rapidly for the first couple of seconds, a very steep slope, and then after it reaches 10 meters per second, remains almost constant. We'd have to identify our knowns and our unknowns. We know that the velocity is varying. We have a zero velocity here, we have 6 meters per second here, we have 10 meters per second here, so the velocity is varying, and so we want to figure out the acceleration. To solve for the unknowns, we're going to look at the tangents of these lines. Here we could see the tangent at 1 second is fairly steep. The tangent at 4 seconds or 5 seconds is fairly shallow. So the acceleration at 1 second, rise over run. So this during at 1 second in time, again we're calculating rise over run, which would be we could take a couple of points fairly close together this time because we want to look at the tangent line. And we have 10 minus 6 is 4, when we have 2.4 minus 1 is 1.4, and we divide it all out, and we get 2.9 meters per second squared. Meters per second divided by seconds is meters per second squared. At 5 seconds, again the rise over run, we have very little change in the acceleration. We could still look at the total time frame involved, and here we get a very small acceleration, 0.3 meters per second squared. The acceleration is not constant because we have two different accelerations. The acceleration is in the direction chosen to be positive because both values are positive. So since we're accelerating in a positive direction, we're increasing speed. Acceleration is measured in meters per second. So this is what we did. We solved for the two different time frames, and we got a good answer. Remember that the acceleration of an object is the slope of the object's velocity, the slope on a velocity versus time graph. On a velocity versus time graph, the slope equals, again, here we have acceleration, and we have these 3 bars, meaning is defined as change in velocity over change in time. Acceleration can occur when speed is constant. Consider a satellite orbiting the Earth at a constant speed. Remember, speed does not have a vector. So even though it's going forward at a constant speed, the direction is continuously changing. Otherwise, it would go off into space someplace to infinity and beyond and keep on going straight. But it's orbiting around the Earth, so the direction is constantly changing. If the velocities change, if the direction's changing, then the velocity has to be changing. If the velocity is changing, we have acceleration. And we'll be answering these on the quiz. We're done.